we got 4 more panels to go. I'm going to start off with our 4th panel for the day. For this panel, we're going to talk about data availability. There's a lot of stuff happening in this space, a lot of optimizations, a lot of changes, and maybe some disagreements too. We'll find out very soon. But to talk about data availability, I want to bring on 3 amazing people. I want to bring on Sreeram from EigenLayer, Illia from Near, and Nick from Celestia. We're going to talk about how and why this is important and the direction we can see things going and some things that we can look forward to in the future. So without further ado, please join me in welcoming Nick, Sreeram, and Illia. Good afternoon. All right. I'm going to try to set up the stage here by doing a brief intro on why this is important and what it is. So we'll kind of go in order first just so we can get different perspectives. But I'd like for the rest of the conversation to be more of an actual conversation between all of you versus one by one. So let's start off with me asking you, Sreeram, why is data availability important?
Data availability basically is the following primitive. So in the on the Ethereum modular roadmap, we offload the computation out to rollups, which basically do the computation and then create proofs that the computation is done correctly. When you do this, it's important to be, for anybody who's observing the system, to be able to access either the inputs or the outputs of the said computation. Because once you have it, you can verify that the computations were done correctly or continue on when the sequencer is no longer around. So this is what gives you the unconditionally correct trust model of rollups. So we need a place where people, or in this case rollups, are able to publish data which is universally accessible. So that's why I think it's very important. And it's important for this primitive to be highly scalable because all the rollups, the total throughput of all the rollups is constrained by the total amount of data that can be returned. So this acts as a fundamental constraint to the entire scaling roadmap.
So what's the nuance here? So it's constrained on the total amount of data being stored on the layer 1 or altogether because it's a bandwidth problem or something?
Yeah, so if you want, the total data that is returned by all the rollups is constrained by Ethereum's data throughput if you wanted the exact security guarantee of Ethereum. So this imposes this constraint, that the total amount of scale is now constrained, and that's why it's expensive to use rollups today to an extent, because they're all paying the cost of data. So by scaling data availability and reducing the costs, even at a slightly lower trust model, is still going to be highly beneficial for a lot of rollups.
So maybe Illia, if you want to add on to this, how does it actually help with scalability?
Yeah, I mean, Sreeram kind of outlined the basic idea. I think maybe looking a little bit from a different direction, I think users and, to many extent developers don't care about specific blockchains, right? They care about actually being able to...
We're gonna start off with the spicy stuff.
I'm all for spiciness here, so yeah, that's why you invited me. And so they care about the value they get from it, right? Be that access to kind of like liquidity markets, be that, kind of assets and participation with others, be that, JPEGs. And so the kind of from this perspective, when we talk about scale, right? Like what we talk about is, making this more accessible to people, making, fees lower, and at the same time being able to what I call unify security, right? What you want is that as a user, you should not need to think about like, oh, I'm going to BNB now, this set of potential failures that can happen to my assets, right? Like that should not be something that as a user and to some extent developers need to care about. And so what rollups kind of introduced is a primitive, right, that enables that, where you don't need to think about the failure modes of the kind of rollup operator, which is another chain potentially, and you can rely that there's a way to recover from the kind of the failures of the operator. But in turn, if you want to get the same kind of level of security, or the maximum level of security we have right now in Web3 ecosystem, which is Ethereum, you do need to pay a hefty fee, right? Which is way higher actually than many of the scalable blockchains in the ecosystem. And so, so the question is, how do you get the best of both worlds? How do you get way lower fees and at the same time have as much security as possible, so that as a user you don't need to care about these details at all, and you can just use applications kind of in a unified view. And so that's where scalable data availability that has a fair amount of security is extremely important, and linking it back to Ethereum as well is an important primitive as well, too.
And maybe kind of just to round it up, Nick, how do you kind of define modularity in this kind of theme? Which pieces here matter for data availability versus kind of being able to actually create more modular architectures for different blockchains to do more than just high throughputs?
So I also just want to touch on like the importance of data availability is because it secures the whole ecosystem built on top of it of layer 2s and rollups. And the issue is that data availability in the current model in which blockchains are built is just not fundamentally scalable. And so to my knowledge, the only actual solution that can both scale data availability in a secure way is data availability sampling. So hopefully we talk about that a little bit more. But how does data availability play into modularity is that in a modular blockchain, one of the insights is that you can decouple data availability and execution. So you don't have to execute all the data that's being processed by the L1. And that enables you to just scale block size and not have state bloat and all these things that have been sort of bottlenecks for scaling blockchains, and instead push that off to the upper layers. And this gives developers more flexibility as well, as they can define their own execution environment, because they're not limited to the EVM or the Solana virtual machine or whatever virtual machine the layer 1 blockchain has. So modularity and data availability go really hand in hand in this new model for how we should build blockchain applications.
Since Illia already kicked us off with that comment, I agree. Users don't care about things like this, but developers definitely do. So what do they need to know about this new world and kind of what changes for them?
So developers care about a few things. One is they want to launch to and have access to as much users and as much liquidity or whatever kind of the related market
Distribution.
Distribution, broadly speaking. And so because of this, they want to have, the security guarantees that if they launch, that their application will be there. It will not go away. It will not disappear because of somebody else. As well as that, as users are, coming in, they have these guarantees around security. And then on the other side, this goes now into a fork, right? Which is you want to launch your own rollup, and then you have a set of criteria you're looking at, or you're launching on a some other chain or rollup, and you figured out like what the parameters are. And there's like a very interesting decision making right now happening, which for a spicy take usually depends on the token launch structure. And so I think that at the end, what you're looking for is the costs overall, right? Because ideally you hide the costs from the transaction costs from the user, right? Right now you cannot do that because they're so high. But it's just they're, for example, near right now it's fraction of a cent. It's like 1/10 of a cent.
This is just a transaction cost, normal transaction.
Normal transaction cost on near is like tenths of a cent, right? So a lot of applications just hide the transaction cost completely. And so for them, it's just an infrastructure cost, same as like AWS or Google Cloud. They just like pay, like stake near, use the proceeds from staking to pay for transaction fees. And then they, generate revenue on this and, it goes into token or whatever the model is. And so, so that's kind of the one really important piece. And so that it defines, the deliverability cost, the settlement cost, like all of those pieces then, get aggregated into your final transaction cost. And so for that, we can discuss like what are the cost structure for data availability, what is the settlement speed, all those things that like technical parameters.
Let's get into it. maybe I think the last thing that'll be helpful for everybody else here to know will be just understanding what your DA solution does. So let's talk about what EigenLayer is, or how you kind of think about yourself in the landscape, and then I want to do the same for Near and Celestia.
Yeah, so we are building a data availability solution called EigenDA, which is built on our restaking platform called EigenLayer. EigenLayer allows Ethereum stakers and node operators to stake and participate in a variety of different services, any distributed system. Nick here was alluding to modularity. In our vision, the number of modules that we need, and usually when people talk about modularity, we think about 2 or 3 modules like data availability and consensus and execution. In our vision, there are maybe hundreds of modules that people may want to build, akin to the software as a service era in the cloud. Like people build many, many hyper-specialized layers, which then concatenate to offer end users and applications the set of properties that they want. And when you have many, many modules, what is very important is that if your end application uses tens of these modules, like an end user application in cloud today uses 15 SaaS services on an average. If you use 15 of these modules, then you are as trustworthy or as the least trustworthy of these modules, because the attack is always like that. What is the weakest link in the chain? So our solution to this fundamental problem is shared security. The idea that there is a common security, a common trust layer coming from staking and node operations, which can then supply trust flexibly to anybody who wants to innovate on these modules. So one of the modules that we are building is to solve the data availability problem called EigenDA. EigenDA is built from first principles as an adjacent data availability layer to Ethereum. It's not a chain. Pretty much everything else you see out there is a chain. And a chain has its own constraints and structure, whereas what we are doing is simply what is the minimal adjacent to actually scale the Ethereum data availability roadmap. And what we do is take some of the best ideas looking ahead in the Ethereum roadmap, like dank sharding, proof of custody, the cryptoeconomics around it, bring it all into a protocol called EigenDA, which we can ship within the next few months. So that's our view. And because of this particular angle, which is that we're not building a chain. When you build a chain, you have to build a consensus protocol, you have to build lots of other things. You have to build a peer-to-peer network, you have to gossip. There's lots of complexities which actually drown out any scale that you can actually achieve. Our vision is very aligned with the Ethereum vision, which is nodes have very low capabilities, but together they all have a lot of capabilities. So EigenDA is built on the principle of exact horizontal scaling. If each node has 1 or 2 megabytes per second and I have hundreds of nodes, the net throughput available is hundreds of megabytes per second. How can we build a system that actually leverages this and achieve the maximum throughput possible? And there's lots of principles. One of the principles, for example, is no node should ever touch all the data. If you want a system to be exactly horizontally scaling, no node, either inside or outside the system, needs to touch all the data. So we're building a data availability layer with a roadmap to scale Ethereum data throughput, to hundreds of megabytes per second. So that's what EigenDA is.
All right. So definitely agree on no nodes should touch all the data. And so Near from the start have been building a sharded blockchain to pretty much scale both, execution, but as part of the execution, you need to scale data availability. And so the Near's consensus itself actually has data availability weaved into it. So when the first step, when transactions are sent, they actually are erasure coded and sent out to other validators in kind of partial way to allow kind of everyone to pretty much start a testing already on data availability for the next block while the execution kicks in. And so this is always was Near's design. And so when we saw kind of there's interest in this way of leveraging, running rollups with data availability, it kind of was pretty clear for us that we can just offer what we already have in the Near ecosystem. And so Near right now, is about 4 megabytes per second per shard. And so we have 4 shards, so 16 megabytes per second of data availability. There's a plan to expand number of shards with some of the launches in Q1. So that kind of allows to have a pretty sizable.
So what's the trade-off that you make when you expand the number of shards? Is it just the piece of finality or kind of data availability altogether?
So right now the limitation has been that we haven't enabled so-called state transition challenges. So this is the same problem that everybody else in the space has. Nobody wants to do challenges on state transition, optimism, Polkadot, nobody wants to. And so kind of a few months ago, we actually switched to implement stateless validation. So similar, actually, looking forward to some of the Ethereum roadmap. And so we're planning to launch stateless validation. With that, we can actually remove the current limitation on we have still some validators that validate all shards right now. So we can remove that going forward from Q1. And so we can start expanding our shards. Now, there's still limits on how fast you can synchronize until you start needing to do hierarchy. But I think that limit is probably like 100 shards ish at this point.
And Nick, I'll let you talk about Celestia as well, and then we'll move on to the other questions.
Yeah, well, what sets Celestia apart from EigenDA and Near is that we've built and implemented and launched what I think the research community agrees is the only actual way to securely scale data availability, which is data availability sampling. The reason for that is that there's a few things. At the end of the day, blockchains are meant to be verifiable systems. And in order to verify DA, you either have to download all the data yourself to hold it in your hand and know, hey, the data is actually here, someone published it, it's public information, or you can rely on a committee, which is sort of what I think, to my knowledge, what EigenDA is doing, and kind of indirectly what I think Near would be doing. Or you can have a system where you erasure code the data and then serve it to clients who can sample randomly from it, and they can have a probabilistic guarantee that the entire data is available while sampling maybe 1% of the overall data. So it reduces the overhead of verifying DA. And that, to our knowledge, I think that's the only solution that's so far been proposed. And so I think, I guess what sets Celestia apart is that it's actually like really trust minimized data availability from the start. And you're not trusting a committee saying, hey, trust me, the data is here. End users can directly verify. And the beautiful thing about that is it enables this new, kind of related to what Sreeram said about not everyone needing to touch the data, it enables this new property that no other chain has had before, which is it scales with the number of users or the number of nodes in the network. And so there's no fixed block size for Celestia. It grows as more people join and start to verify and sample the underlying block.
Some disagreement here. Data availability sampling, actually, Celestia founders are one of the pioneers of data availability sampling, and it's actually a really cool technology. But it only helps when you are a rollup on Celestia. So you have to build a native rollup on a chain, and then if all the validators of Celestia collude and make the data unavailable, you as a user of that rollup can sample the data and know, oh yeah, the data is not available. That's what Nick calls self-verifiability. I think this is a really cool property. I want to emphasize why we didn't actually go take this path. Because if you're building something on Ethereum, everything is just a committee. Celestia is just a committee as far as Ethereum is concerned. Ethereum cannot do data availability sampling on Celestia. Ethereum trusts that a majority of Celestia nodes said that the data is available, and then makes progress on the rollup contracts. So because we built our protocol to be native to Ethereum and as an adjacent to the Ethereum rollup roadmap, we decided to make data availability sampling a secondary feature. Why do I say it's a secondary feature? There are some features which have to be built in protocol. It has to be inside the protocol to actually for a feature to For example, nobody can go and change the Ethereum block size. But you can build a new wallet by yourself. It's permissionless. Data availability sampling on EigenDA is exactly the same thing. Anybody can build a sampling mechanism on top of the EigenDA protocol because it already has erasure codes. I think you can also build it on the Near protocol because Near also has an erasure code. Erasure coded commitments is what enables data availability sampling. But once you have it in the protocol, anybody can build a sampler out of protocol. But from Ethereum's viewpoint, everything is just a committee.
There's actually an approach to have data availability challenges on Ethereum.
Yeah, there has been some recent talk and announcement about it.
Yeah.
So, I think this is one thing we may all agree on. The idea of a data availability challenge. Do you want to talk about it? Nick seems eager.
Well, someone explain it, and then I'm just going to tear it apart.
Okay, let me explain it, and then Nick can tear it apart. Okay, so the idea of a data availability challenge is somebody makes a claim that the data is available, and if you don't agree, just like in an optimistic rollup, somebody makes a claim that the execution is X, and if you don't agree, you go and post a bond, and then you run the execution on chain and check whether it's correct or not. Data availability challenges extends the same idea to data. Somebody claims that the data is available. You disagree, you go and raise a challenge on Ethereum and see whether the data is available or not. That's a data availability challenge. I'll let Nick tear it apart.
Well, the problem with data availability challenges is something that the research community has known since 2018. It's called the fisherman's dilemma. Essentially, it relates to the fact that data withholding is unattributable. So for an outside observer, when someone withholds data, then you can't actually objectively prove that data is withheld because that person can always just later reveal the data. So now you're stuck in this situation where anyone who raises the challenge can basically be trivially disproven. And it relates also to another thing, which is that, and which is kind of related to what Sreeram was talking about, of every DA solution external to Ethereum is just a committee. That's true. And what I would add, though, to that is that any committee that is, or any DA solution needs to have a native asset to give it any cryptoeconomic security, because same reason why data challenges don't work, you can't prove on-chain that someone did with data withholding, so you can't slash someone. For example, if they staked ETH on this DA solution, you cannot prove that, hey, you should slash this person staked ETH. The only way to slash for data withholding is socially, and socially slashable collateral has to be native to the data protocol, which is why, for example, Celestia did not pursue some sort of like ETH restaking type of way to secure itself. It actually merits and requires a new token to do that. So.
Yeah, but I want to add that that has nothing to do with data availability sampling. Near protocol, for example, if data was withheld on the Near protocol, a majority of validators collude, and they make a claim to the Ethereum protocol that the data was available. The Near protocol will stall, the blockchain will stall, and then the validators will coordinate a social fork, forking out the Near validators who made this wrong claim, and therefore they'll be slashed. So there is a cryptoeconomic guarantee. But addressing the cryptoeconomics of EigenDA, do you want to add anything on this?
Well, I think the interesting part there is our partnership to actually plug in Near with EigenLayer, such that on top of the Near security, which is whatever, like $700-800 million worth of cryptoeconomic security on Indeed, that like pretty much if at least 1/6 of validators are honest, like there will be actually recoverable data across the whole all shards. On top of this, then we can kind of leverage restaking on Ethereum to have the restaking validators to pretty much sign on and validate as well their erasure coding and commit that signature as well. And so this actually gives us more security. And from Ethereum perspective, actually unifies as well that, it's using very similar underlying security, which is why the spicy question is it nearer than the EigenDA?
Okay, so I'm going to address both the things together. What is the cryptoeconomic security of EigenDA? So EigenLayer is this restaking protocol, and the way it works is you stake ETH and then you borrow economic security. But what does it mean to borrow economic security? What is this like new object? It's basically saying that if there was a violation that happened on your protocol, if you can write an on-chain slashing contract. What is a slashing contract? It specifies the conditions of misbehavior under which your ETH will be taken away. If you can write an on-chain slashing contract, and then you can basically slash somebody's ETH, and what you're borrowing is economic security, means that if your service went wrong, you will be able to slash this amount of ETH. So unless, so that gives you a certain amount of guarantee, an economic guarantee that your service won't go wrong. Okay, so now coming to EigenDA and why it's not so simple to borrow economic security for EigenDA, which is a point that I think Nick is trying to allude to, is when you're running a data availability system, there are two things you're doing as a data availability system. Number one, you're downloading and storing the data, because it's data availability, but you're also serving the data. These are two things you have to do. And what we have with EigenDA is a mechanism for slashing for data, not storing data. It's called proof of custody. So this proof of custody is a mechanism which basically ensures if you hold the data, then you have to do certain kind of computation with the data, and then and along with some private secret, and then post a proof, directly or indirectly, that you've done that computation. So if you're not storing the data, you will get slashed. But the problem is that if you may store the data and not serve it, right? So if you may store the data and then not serve it, why may you not serve it? There may be two reasons. One is you're lazy and you don't care and you don't serve. Or number two, you're just colluding to adversarially withhold data. And so here's where the trust assumptions of different protocols there's a lot of nuance, so one has to think about it carefully. EigenDA is constructed on the dual pillars of economic security and decentralization. It's not a purely economic security protocol. What do I mean by that? When you rely on economic security, you're only caring about how much money is staked. Do you have 100 million or you have 1 billion? It doesn't matter whether one guy stakes 1 billion, or thousands of people each stake 1 million each. Because if that thing went wrong, I'm going to be able to slash 1 billion. So this is called economic security. There's another pillar of blockchains, if some of us have forgotten, it's called decentralization, right? Which means there are many...
What's that?
There are many distinct operators.
We switch to one server now for everything.
So the idea is that in decentralization, there are many, many operators, each of whom should be able to operate with very limited resources. Many operators, and they're all independent and therefore are unlikely to collude. So EigenDA is built on the assumption that if that is the case, if you actually have decentralization, which is lots of node operators who can actually don't collude, then you get the following mechanism, which is that if you want to serve the data, there is a competition among the different nodes to actually serve the data, because data is widely dispersed. No one guy holds a monopoly on the data because the data is erasure coded. You can download it from any 10% of the nodes, depending on the erasure ratio. In Near's case, any 1/6 of the nodes. So it's a parameter. But what that does is, as long as everybody, 100% of the nodes don't collude together, there is always an incentive to serve the data. That's the cryptoeconomics of EigenDA. Because it's nuanced and has all these things, we think of EigenDA as a special service, and whereas economic security can be easily borrowed for any other kind of service, data availability has to be much more nuanced. And so that's how
So I just want to add, I think one of the third and probably most important pillar for blockchains is verifiability, right? Sure, you can have a committee and make it more decentralized, but you're still making an honest majority assumption on that committee. And that is not why we're building blockchains, to get out of that kind of system. Otherwise, it's similar to Web 2, where you can just have a consortium of a bunch of companies sign everything. And it's hey, we trust that. That's not what we're here for. We're here for verifiability by end users. And so that's again, the only solution that can give end users verifiability is data availability sampling.
You get the benefits of data availability sampling, you have to be a Celestia rollup. You cannot be an Ethereum rollup and then use Celestia for data availability and get these benefits. So, that's a real power of having an integrated data availability system. So I said EigenLayer, EigenDA is designed as an integrated or like an adjacent data availability to Ethereum. Celestia is designed to be very powerful, this special property of a data availability sampling, because it's integrated with consensus. That's what gives it the superpower that actually if data is unavailable, the chain will fork along with it. But unfortunately, this benefit doesn't translate when you're an Ethereum rollup.
So my next question is, what is something that you disagree on? I thought that was the whole panel. Actually, most of the time when we hear these things, one thing I've noticed personally is that a lot of this talks about the economic security of the protocol, which is kind of bundled into a binary: will it exist or not, will it fail or not? But this particular thing is especially important to developers on what exactly is being stored and how does that compromise anything that I'm building, if I'm building a company or protocol, anything else on the successful side. So kind of forgetting the cryptoeconomic piece of it, can you give us a way to think about what does it mean to cost sample and just actually store that information, and how do I think about the cost for storing this, whether it's my rollup data or my kind of app data that's being kind of positioned into Celestia or EigenDA or anything else? How should I think about what is going to cost me? How does that change over time? Who's paying for this? Who's providing these storage services? What's that incentive model? And kind of how does that evolve?
I mean, I'll take a spicy take here. I think the reality is...
We have to first explain what it is before you kind of make any comments. Like, I want to still understand what's a good intuition for how much does it cost with a DA solution versus putting call data on Ethereum, just so we have some, in a way, dollar figures or even like multiples.
I'm not sure exactly what the per megabyte cost is like of posting data to Ethereum, but earlier today on Twitter, there's a team building a game on Celestia, and they did a comparison of like if they would do it on ZK Sync, it was like 20 cents a transaction. Can't remember, they went down, and then Celestia, they even actually running on Solana was like, on the Neon EVM was like 0.00015, and I think Celestia was 0.00008 or something like that. So like orders of magnitude less expensive as of now, and hopefully actually cheaper because we're planning to decrease the sort of min fee that we've set. So I think one of the beautiful things about this is that I think
Could you define what the fee is? So the fee is for what particularly? One-time cost? Is it a rent?
Oh, right. So, okay, first of all, it's really important that people understand that storage is the wrong mental model to use when you're thinking about data availability. It's more about publishing. And something that you publish is just something you pay once. It's like, it's like putting an ad in the classifieds of your newspaper. Like it goes in, it's there, and then it goes away. It's not meant to stick around. So there's not like this recurring cost of like, oh, I need to keep the data around indefinitely. In fact, like all data availability solutions have pruning like built into them for that reason. And so I can't remember what. Oh yeah, I think one of the cool things about this is I think that cost has been a major blocker to scaling, obviously, Ethereum L2s, and there's a lot of use cases that have not been built. And there's this idea in economics of induced demand where, imagine like electricity, what costed like, I don't know, $50 per kilowatt hour or something. All these use cases like running a microwave or, I don't know, charging your electric vehicle or whatever would become infeasible or just not worth it. And when you drop the cost of electricity to, let's say, like, a cent per kilowatt hour, all of a sudden people are going to use a lot more electricity because all these new use cases become feasible and useful. And so I think that's what I'm excited about for Celestia launching blobstream, which allows people to run Ethereum L2s using Celestia as DA. All the other DA solutions will unlock all this like pent up demand and use cases that have been held back. So I think and the end user saves money. I also think the developer can reap more of the execution fees for themselves, so the developers can actually like sustain their business.
Yeah. So to second that, we're 8,000 times cheaper than Ethereum. So
That's a big number.
yeah. So where you're right now, your base or OPs or Arbitrum is like 40, 50 cents. We are, 4 zeros, 1, something like that, or 5 zeros, 1. And so I think the interesting thing here, what happened, that's what I mentioned. I think developers will just cover this fees, and like on Near, again, you can just cover it from the staking rewards. The real costs now kick in. And the real costs are indexers and all of the infrastructure you run around this to actually serve this data to the users to properly interact with your apps. And I think that's where we kind of forget, like, yes, data availability is the publishing part. It's making sure that, people can verify, can run the indexers, can run all this infrastructure. But now, if you want to spin up Etherscan for yourself, it's $500K a year, right? And that's a real costs. So I think like the important part here is to think not just about the blockchain costs now, especially now, but actually about the full cost of developing apps here. And this is where sometimes it makes sense for you to launch a rollup, and you will have like 2, 3, 4 million a year of like extra costs on the services. And sometimes you should use a layer 1 that has all this infrastructure already integrated, and you don't need to pay this extra cost. So that's what I meant. Like there's a decision actually fork there around like what the ecosystem you're building, how you actually structuring your application, and what are the other pieces that you need around your infra.
Anything to add?
Yeah. One of the things we think about a lot is the economics around data availability. The principle that we are building out of is actually, people think a lot about block space as a kind of fundamental constraint. We're building for a world where like block space is not a constraint. And to have an avocative analogy, you can think of like, is there a concept of cloud space? Like if you wanted more like compute, AWS will create more compute for you. Right? So there is no concept that this is the cloud space limit. There's no cloud space limit. Cloud will stretch itself to accommodate whatever is needed. And one of the mechanisms, one of the important economic mechanisms by which this happens is reservation, right? If you go to AWS, you can either have a spot instance, you can randomly go and try to get an instance at the moment. Sometimes there won't be instances, but you can reserve an instance. It's just for you for the next 1 year. EigenDA is built on this dual economic model of spot bandwidth and reserved bandwidth. Because as a rollup, you want to have the cost basis of your rollup to be more predictable, right? You're running an airplane company, you want to know what the input costs are so that you can charge your users. So it's the same thing when you're running a rollup company. So EigenDA is built on this as one of the principles, which is that you can reserve data. And this allows us to provision more data because more people are using it. So that's number one. Number two, we have a mechanism where rollups can pay for reserved data bandwidth in their own native tokens without taking exchange rate risk. Right? If you're a layer 1, one of the really cool economics that you have is you pay a certain fraction of your token for like all your validation. But if you're a rollup, you suddenly like have this like obscure economics where you cannot say that you're only paying a fixed fraction of your own token for data availability. So EigenDA is built on reservations through native tokens. Number 3, EigenDA is built on dual staking. So you not only can stake ETH, but also provide additional utility for your own rollup token by allowing that as a staking token. EigenDA allows this as a native feature. All these features are fundamentally economic features on the data.
So maybe the last question here, which hopefully we can make some quick predictions on. How do you kind of think this economic model pans out? I mean, is this just going to be subsidized for other potential revenue sources? Everything becomes free because everybody has to then take on the indexing cost, which is the real kicker. Or are we saying we kind of find a stable equilibrium here? Like, what does like 2 years from now data availability look like?
I mean, I think the reality is the cost will go down to whatever the compute storage costs are.
Yeah, like
Plus a little bit of
and it gets
margin.
cheaper every 2 years.
Yeah, and so I think that's why, so for example, on Near, why I'm saying you can just stake and pay from staking rewards is because that actually aligns the cost structure, and we have actually a way specifically where you have your own token, you can just distribute this token to the stakers who are staking on your node that pays for your transactions. So you can be literally same idea. You can be in your token economy and pay for transaction fees underneath. And so Aurora been working like that as well, where they cover transaction fees for first 50 transaction fees for users. But like that's model like kind of just built on top of, as you said, not embedded in the protocol, but just built on top. In general, I think we'll be going forward where we'll kind of start moving away from direct transaction fees by the user. When you have, like, again, we're talking about you'll pay something like $1,000 per like 10 million transactions or something like that, and so like you'll need a lot of transactions yourself, right? And so we already have this on Near, even like with we have an app that has like 700,000 daily active users, right? And they cover all their transaction fees from staking. So like that's totally workable model. So I think like the main costs will start moving up to like actual infrastructure that it does need like a lot more capacity, and with blockchains I think we'll see kind of compression fees pretty dramatic.
Any other quick comments on this?
There's a blog post written by Chris Brodisky of Placeholder from back in 2019 where he just talks about like the economics of protocols generally, and he has a quote that I really like, which is that protocols should strive to be minimally extractive but globally produced and consumed. And so I think the goal of a data availability solution is to be to produce at scale and sort of like sell block space at massive scale, and hopefully almost at cost, to be like minimally extractive, or like not sort of like unnecessarily extractive, I should say. And I think that's kind of the philosophical alignment of Celestia. Is like it's more like kind of like AWS. It's like AWS doesn't win by having only 10 computers that like, or like a tiny server data center that everyone has to compete over and price gouge people. It's like, no, let's expand capacity as there's more demand, and just make sure that there's some amount of margin that is charged to make the whole thing economically sustainable.
Awesome. That's a perfect note to end on. Nick, Illia, Sreeram, thank you so much for an amazing conversation.
Thank you.
Thank you.
Here. Thank you.
All right, up